In this lesson, we'll continue our discussion of muscle tissue by taking a look at how we generate tension in a whole muscle. In our previous lessons, we had looked at how we generate tension in one muscle fiber. Now we want to take that a step further, right? We're going to look at all the muscle fibers together in one muscle and show how the entire muscle generates tension. Right? So the amount of tension produced by a whole muscle is determined by the number of individual muscle fibers contracting. Right? So if you're going to do heavier work, you're going to have more muscle fibers contracting within a muscle. Or if you're going to do lighter work, you're going to have less. For instance, if you went to the gym to work out and you were going to do your biceps and maybe you're going to do a bicep curl, right? If you pick up a 5 pound weight to do that curl, in your biceps, a certain amount of muscle fibers are going to contract to lift that 5 pounds. But if you now switch from a 5 pound weight to, say, a 20 pound weight, you're going to need more muscle fibers to do that work. Okay? Regulating the amount of muscle fibers contracting will result in smooth muscle movements, right? So as we control the number of muscle fibers that we engage, our movements are going to be more smooth and even coordinated. An example of this may be, let's say you went into the refrigerator and there is a container. Let's say somebody made some nice iced tea for you, and you thought that they just made it so the container is full and you can't see the amount of liquid in it. So you go to grab that container and you assume it's full, but it turns out maybe it was only a quarter full. So you probably used more muscle fibers than you needed to lift that container because you thought it was heavier, and it may have resulted in a more jerky type of movement, because again you misjudged how heavy it was. So there's an important definition that I'd like you to know. This is known as a motor unit. Very simply, a motor unit is one motor neuron, right? That's the nerve cell going to the muscle fiber. It is one motor neuron and all of the muscle fibers that it controls. Now, motor units vary in the amount of muscle fibers they control. In some instances, one motor neuron may control a few muscle fibers, but in other instances, one motor neuron may innervate thousands of muscle fibers. And here's an example. Our muscles that are in our eye and our hand, one neuron innervates about 4 to 6 muscle fibers. That gives the nervous system much more control over these muscles, right? When you move our eyes, right, we can move them very specifically and in certain directions, right, real precise. Or hand movements, you think about people that are surgeons or people that do music and just different things with their fingers, right? They have much more control because we have more neurons going to the muscle. But take a muscle that's more like weight bearing, our thigh and our hip muscles, like the hamstrings, that type of thing. Here, one neuron innervates 1,000 to 2,000 muscle fibers, right? Because these muscles do more gross movements. They're not doing more precision type of work. Okay. Now, here's another, that last comment's also important here. When this motor neuron fires, all of the fibers in that motor unit contract at the same time. So what am I talking about? Let's go to a picture. So this is a little bit advanced. This is a cross section of the spinal cord. And we see here that there's a red, a blue, and a purple cell body for 3 different neurons. These cell bodies live in this part of the spinal cord. We're going to learn when we do the nervous system, right? This is called the ventral or the anterior horn. You don't have to know that now, but that's where these cell bodies live. Then the axon comes out. It's going to go into a spinal nerve, and then the axon will follow this red one, is going to innervate muscle fibers in the muscle. So here they're showing the bicep, and they're showing some muscle fibers in the bicep. So this red neuron here, if you notice, is only innervating some of the fibers, and they painted them red. 1, 2, 3, 4, 5, 6. That means when this red neuron fires, those 6 fibers will contract. The blue one, is going to go down through the spinal nerve and innervate 1, 2, 3, 4, 5, 6, 7. The blue one is innervating 7 muscle fibers in this example, right? And those are the muscle fibers painted blue. And then the purple one are going to do 1, 2, 3, 4, 5, 6, 7 also, those 7. So when the purple one contracts, only the purple fibers are going to contract. So again, if you were going to go to the gym to work out your bicep, let's say, and you were only holding a 5-pound dumbbell, again, this is an example, maybe only the red neuron will fire, causing contraction of those 6 muscle fibers, and that's enough force to do the curl at 5 pounds. But now if you change to the 20-pound dumbbell and only the red neuron fired, that's probably not enough tension in the muscle to lift that weight. You would have to also maybe have the blue one and the purple one fire to do that amount of weight, or maybe even more so. All right, but the concept right now is, before we look at that, is that a motor unit is one motor neuron, let's say the red one, and the fibers that it innervates, these red ones here. And when that red one fires, only the red fibers in this example will contract. Right? When the blue one fires, only the blue fibers in this example will contract, and so on. Okay, so this is a really important definition. The motor unit, again, is a motor neuron and all of the muscle fibers it controls. And again, all those fibers in the motor unit contract at the same time. They're going to contract together. All right, so here they're actually showing you when you apply tension to a tendon, right, in a muscle, the first motor unit will fire, creating a certain amount of tension, and then that one will take a break, and then the second one will, and we get a certain amount of tension, and then the third one we get a certain amount of tension, and we get a relatively stable or constant amount of tension when we have like a sustained muscle contraction. The motor units actually take turns. Okay, so I had given an example before of lifting a 5-pound weight and then increasing that weight to 20 pounds. So obviously from 5 to 20, we need to add more muscle fibers. That concept of increasing the number of muscle fibers that we need is known as recruitment. Right? So this is an increase in the number of active motor units. Again, going back to my original example with the 5-pound weight, maybe only the red motor unit fired. Then maybe we went to 10, right? Then the red and the blue fired together, and now we go to 20, right? The red, the blue, and the purple will fire. We're adding the number of motor units so that we ultimately get more fibers. That concept is known as recruitment, and this produces a smooth, steady increase in tension. Now, you can get maximum tension in your muscle when you recruit all of the motor units. So all of your motor units are causing the muscle fibers to be in complete tetanus. When you have that, you can only sustain that for a very short period of time. More prolonged, sustained contractions, they don't produce maximum tension, and we see that the motor units are allowed to rest in rotation. That was my example over here, right? So say you're doing like a sustained contraction, right? The red one will fire, then it will rest, and then the blue one will fire, then it will rest, then the purple one will fire, then it rests, and then the red one goes again, so that we end up with like a generally a sustained contraction here, even though there's a little bit of waves, but it's just a general sustained tension in the tendon because the motor units are taking turn. Right, so sustained contractions, they don't give us the full maximum tension, but they do have some kind of taking turns of the motor units, if you will. Okay, there's another concept now that you know what a motor unit is, something known as muscle tone. Right? If you were just sitting at your desk right now, listening to this to this lesson, and it just kind of touched your bicep, if you weren't contracting it, you would feel that your bicep muscle has a certain firmness to it, right? It's not like a bag of mashed potatoes. There's a certain amount of firmness, even though you're not contracting the muscle. The reason for that is in a resting muscle, all of our muscles, some motor units are always active, even though we're not moving. So muscle tone is the normal tension and firmness of a muscle while at rest. Right? So without causing any type of movement, the motor units are actively stabilizing the position of your bones and your joints. They're maintaining your balance and your balance and your posture. Okay. If you have increased muscle tone, you actually end up burning more energy because we'll learn that in subsequent lessons. In order to have sustained contractions, we need to make ATP. But the concept for this slide is this: even though our muscles aren't moving, right, you're not producing any body movements, there is a certain amount of tone, contraction that you don't notice because the motor units are always firing. Right? And that is known as muscle tone. Okay, let's take a look at a couple different ways that muscles contract, and I want to show you some different types of muscle contractions. The first type of muscle contraction we're going to call isotonic contractions. When your skeletal muscles contract and the muscle changes length so that we produce movement, this is known as an isotonic contraction. It turns out there's two types. So there's an isotonic concentric contraction. This is where the muscle tension, right, the amount of force that we generate in the muscle is more than what you're trying to lift, which is known as the resistance or the load, and it results in the muscle shortening. So if we go to this example here, if I go back to that example of the bicep curl, here's your bicep. Whatever the weight is here, if we can generate more tension in this bicep so that the muscle fibers, I drew these arrows here, shorten, right? The muscle gets sliding filament theory and the muscle shortens, we end up getting movement of the joint and we can lift the weight. This is known as a concentric contraction. But watch this. If we took that dumbbell and you slowly let it down to put it back on the rack, you would still be contracting the muscle as you slowly let this down, but the muscle fibers would be lengthening. This is known as an eccentric contraction, right? The fibers are going to lengthen, where a concentric contraction, the fibers shorten. And in both examples, the elbow is moving. Here, right, we're flexing the elbow. Here, we're extending the elbow, right? Because we slowly let the forearm down. We're still contracting the bicep, right? There's still tension there. You can try it, but you're letting the muscle fibers go out. This is known as an isotonic eccentric contraction, right? The muscle tension is less than the load and the muscle fibers elongate. Okay, so isotonic concentric contraction, the fibers shorten and we get movement, right? The joint's moving. Now, if you let that dumbbell down and you're still contracting that muscle, as you slowly let that dumbbell down, you'll feel tension in your muscle, but the fibers are lengthening. That is an eccentric contraction. The other type of muscle contraction we get is when a muscle contracts, but there's no movement. The muscle doesn't change its length. This is known as an isometric contraction, right? The skeletal muscle develops tension that never exceeds the load. The load is so great that we don't produce movement. And for those of you that do like planks, and I'll show you a picture in a moment, when you're doing a plank, you're doing an isometric contraction. So let's just say this person here is grasping a fixed bar, right? This bar is attached to the wall, let's say. So no matter how strong he is, he's not gonna move that bar. So as he increases the contraction in the bicep, he's going to pull his hand up against that bar, but the bar is not going to move. The resistance is greater than the tension that he can generate. The muscle is contracting, but there's no movement. This is an isometric contraction. The fibers do not shorten. Right? The fibers will not shorten. An example is a plank. So when you're in a plank position, you're contracting all these muscles, but you're not moving, right? So you're contracting these, especially your postural muscles here, isometrically. Okay, just a couple other minor physiological concepts. The relationship between load and speed, they are actually inversely related. So when something is inversely related, it means when something goes up, the other thing goes down. For example, the heavier the load, right, the more weight you try to lift, the longer it's going to take for movement to begin, because again you have to engage more of the actin and the myosin, right? So it takes longer, opposed to the lighter the load, right, the quicker something is going to go, right, the faster it's going to be. And we always need to overcome the tension before shortening can occur, right? So the physiological concept is this: load and speed are related, right? The heavier the load, the slower it's going to be, right? The speed is going to be, it's going to take longer because they are inversely related. And finally, for this lesson, so once a muscle fiber, or muscle I should say, has contracted, it has to go back to its original shape. So there are some things that control that, right? So this is about muscle relaxation and returning to its normal resting length and shape, right? If you make a muscle with your biceps and it bunches up and bulges up, you don't want it to stay like that. It's got to go back to normal after you're done contracting it. So there are elastic forces, right? The tendons actually recoil after the contraction, and that helps to pull the muscle belly back to its original strength, shape, length, I apologize, back to its original resting length. If you contract your biceps and then you relax it, and you can then contract your triceps, which is the opposing muscle on the opposite side, you contract your triceps, that's going to straighten your elbow, which stretches the bicep. So opposing muscle contractions will help things to get back to normal. And then our good old friend gravity, right? That's going to help to bring our muscles back to their normal resting length. Okay, so that concludes this lesson on how we generate in the whole generate tension in a whole muscle. Again, some of the important concepts are the motor unit. Right, it's important for you to know it is one neuron and all the muscle fibers that it stimulates. And then the concept of recruitment is very important. As we do more and more work, we need to recruit more motor units. And then just to review, especially the different types of contraction. Concentric contractions, we're going to get joint movement. If the muscle fiber is shortened, that is known as concentric isotonic contractions. If the muscle fiber lengthens, that is known as eccentric isotonic contractions. And then finally, if the muscle fibers do not shorten, that is known as isometric contractions.